Okay, so let us go here to here. So some folks have commented on the fact that they are unable to be present on Thursday. So I have created 2 more days of observing. That goes here. The first one will be on Monday, the 7th. And then the second one will be 3 weeks later on Monday, the 28th. And then we're almost done, folks. So this is us currently in week 10. And I only have 6 more weeks. So that's a month and a half. So we're going to talk about Pluto. We'll talk about small bodies, such as asteroids and comets. That may leak into this idea of how comets delivered water to Earth, for example, how collisions may explain a lot of the weird stuff we see in the solar system. And then we'll talk about the formation of the solar system as a whole. We'll talk about exoplanets, planets outside of our solar system. And then we have some like bonus days. So we can do one of 2 things. You can be like, oh, I really liked when you were talking about exoplanets, just keep talking about them. Or you can be like, what about like astrobio? Or what about these other planetary science topics that you haven't told me about? So sometime in here, like week 13, I'll just pass, I'll either pass around a piece of paper or you can write it on a notepad, just 5 topics, and then I'll crowdsource those topics. They can be, within reason. I'm not going to do like fashion. It'll be a topic of your choice towards the end if we have time. Is that reasonable? Would you prefer that over like a help session? Cool. We'll check in a while. Okay. Let's get away from the idea of exams. I still have some exams here. I'm sorry if I'm going to get your names wrong. Janaline. Marissa Bell. Okay. Caesar. Madison. Tim. Okay. No, I get it. No worries. No one wants to come to class after the exam gets back, right? Okay. So today we're going to talk about Pluto. Is that right or wrong? Oh, excuse me. Sorry. Okay. So let's do that. Any questions before we move away from this? Okay. Some folks successfully argued for more points. Not everyone did. But it's not everyone walked up. Everyone who walked up got a little bit of points. Is this work? Yes. Let's go. Okay. So I got a new battery. We're gonna have this replaced with the POS. We have a junior scientist with us today, so I'm gonna try and be respectful of that. Let's talk about poor Pluto. So we're going to start this off by trying to name items in the solar system. I'll go first. So the sun. Any object in the solar system. Mercury. Mercury. The moon. Mars. Neptune. Earth. Jupiter. Jupiter's rings. I'm not going to give you that one. Io. Okay, I like that one. Ganymede. Callisto. Eris. Ooh, okay. Someone did the reading for today. What's that one that goes back? I don't know. That's not the point of this exercise. Triton. Titan? Yeah. We ran out of planets. You went to moons really quickly. So you've been naming a lot of moons. You're missing a lot of planets. That's okay. Uranus. Uranus? Object, right? Yeah, just objects. Yeah. Pluto, good. Well, I was looking for a lot of them. I was hoping we'd go through the planets and then through some of the moons. And you hopefully would throw Pluto in there. And so this was very controversial when I first taught this class in 2016. It's less controversial now. People are accustomed. Some people were born after Pluto was demoted. So, some people lived through that whole process. Before we talk about why Pluto was demoted, why did it lose its position as a planet? We're going to talk about the history. So this is going to be like a lighter class. We'll learn a lot less physics. Ooh, thank God. Let me show you two fun things that I found online. You guys see this?
Yes.
What is it?
Sun.
The sun with a smiley face. Yes, that's exactly correct. So this was the sun yesterday. This is a picture from the Solar Dynamic Observatory. And these regions here are cool, so they're dark. And these regions here are light, so they're
Super.
very good, very, very hot. And in fact, this is what the surface of the sun looks like. You don't see it that way. That's because our eyes don't see this type of light. But the surface itself not only has this idea of something that you could stand on, you can't, but it looks like you could, and then all this really hot atmosphere outside of it. It has these cool loopy-de-doops, which are essentially magnetic fields coming out of the surface and then back in. The places that they go back in are the cold parts. Places that they come out tend to be the hot parts. Okay. So that was one thing that happened. Then this happened today too, or at least it was released. What's this on the left-hand side and what's this on the right-hand side? What's the difference? What?
Before after.
Yeah, it's a before after of what? Yes. Where? What's that? The moon. That's a good guess because these are very gray. But it's not the moon because it doesn't have enough craters. Moon's heavily, heavily cratered. This one is probably Mars. It is in fact Mars. What happens is we fly over Mars a lot, something called the high-rise imaging system. It's very high resolution, high res, high rise. And so this is what you see on the left-hand side. This is what you see on the right-hand side. And there's some cooler close-ups there. What's this black stuff that's moving away? Exactly. We call it ejecta. So this is the stuff that's been ejected, the debris, the ice, the dirt, and it's thrown onto this fresh ground here. Pretty cool. Doesn't happen very often. Okay. Question? What is the Kuiper Belt? Is it A, a disk of rocky bodies between Mars and Jupiter? B, a disk of ice bodies outside the orbit of Neptune? C, the sphere of comets that surround the entire solar system? Or D, the planet moons of the outer planets orbit in? When you're ready with the fist. You ready? Okay, let's vote on 3, 2, 1. Okay. All right, so not everyone did the reading. That's okay. So the Kuiper Belt is not the rocky bodies between Mars and Jupiter. What's that called? The asteroid belt. Yeah. So that's that thing that in Star Wars they fly through, right? They're trying to dodge all the rocks. Huge exaggeration. None of those rocks are anywhere close to one another. You could fly through the asteroid belt, you wouldn't hit anything. You would be flying very slowly. This thing here we haven't talked about yet. It's called the Oort cloud, or an astronomer who saw a couple weird comets and predicted that there was a giant cloud of comets, and he was right. Cool. Wish I was around when you could just predict stuff and be right. And this thing doesn't exist. This bottom one, the plane that moons of the outer planes orbited, that's not a real thing. So that's I had to come up with something to not have it be threes. Okay, so it's this object here. It's a disk of ice bodies outside the orbit of Neptune. And that's what we're going to be talking about today. So we want to talk about how Pluto fits into our solar system. We're going to talk briefly about, not briefly, we're going to talk entirely about this spacecraft called New Horizons and some stuff that we've learned since. Here's the planets. You can do it that way, but when you you seen this before? Mnemonic to remember each of these by. They're dumb, but if you get rid of Pluto, then you can just get rid of pizza and just turn it into nachos, right? Okay, boring. All right. So what's the definition of a planet? Am I a planet? Didn't know I'd get assaulted today. Okay. Is Pluto a planet? Raise your hand if Pluto is a planet. How many people are Pluto purists? No one. Wow. Okay, so I don't have to convince any of you. So it's not. So it does a couple things. It orbits the sun. Cool. Do I orbit the sun? No, I'm not orbiting the sun. I'm on Earth. Okay. It's big. I'm not gonna have. Okay. Specifically, big enough so that its gravity pulls it together into a sphere. Now, I am cylindrical, if I'm being generous. I'm not spherical yet. Okay, so I am not a planet. Okay, so in 2006, they decided, not a planet. Why is this happening? Okay. You can read the full one here. It's in orbit around the sun. It has sufficient mass for self-gravity so that it assumes a round shape, right? And this one is really important. It's cleared the neighborhood around its orbit. We're going to talk about this more when we talk about formation, but in the context of what we're thinking about here, we're wondering, does it have all of the stuff nearby? Did it gobble up all of its friends, right? So you think about the difference between, say, Venus, the Earth, and Mars. There's not just a bunch of debris in between, right? So in between, say, Mars and Jupiter, there is a bunch of debris. So no object in the asteroid belt could be considered a planet because it's got a bunch of debris with it as well. Okay. So we have to have another word. A dwarf planet is a smaller planet, still in orbit around the sun, nearly round, but has not cleared the area around its orbit. Okay, that is the primary difference. And of course, it's not a satellite. We made it, or it's a moon, doesn't count, right? Two versions of satellite. Satellite can be anything orbiting anything else. So for example, our moon is a satellite of Earth, the OG satellite, right? All other objects except satellites orbit the sun shall be referred to as small solar system bodies. Okay, so what's the main reason that Pluto is declassified? Said A, it's too small. B, it's too far out in the solar system. C, it's made of different materials than the nearby planets. Or D, its orbit is tilted. Let's vote on 3, 2, 1. Okay, most people are saying 1. We'll talk about this in more detail. Okay, so Pluto was discovered in 1930 by this dude. He just spent a lot of time at night looking at the sky. Cool. Found an object moving. So what you're looking at here is the same sort of stars. You look on the left-hand side, see these little triangle stars? You see that? And then you see these ones up here, same stars. Same stars. Notice any differences between the two pictures? I warmed you up with that crater, right? Got you ready to that. No, okay.
There's that one like that. Yeah.
This one, right? Or this one?
Oh, yeah. That one.
Okay.
That's
Yeah, so this one goes from here to there. That is Pluto. So you look at images of the night sky in the same place over and over and over and over and over, and you try to look, hey, you don't see anything moving. And then you can find Pluto. Okay. And this is 1930s, so we didn't have super good telescopes, but we had good enough to find finally be able to see it. You can watch it long enough and you can figure out exactly how it's moving on the sky. And then you understand how gravity works. And so you can you see a little bit of its motion. You can figure out what its orbit might look like. And the first thing that people notice about Pluto is a little funny. Okay, so this is the sun here. There's Mercury, very elliptical. The Venus, the Earth, Mars, they're all basically fit into this little spot right down here. Gotta shrink them down to be able to put them on the graph. Then you have Jupiter and Saturn, Uranus and Neptune. And then you have Pluto doing this. Okay. So sometimes Pluto is closer to the sun than Neptune is. Even sometimes it's farther. Sometimes it's in the plane, sometimes it's out of the plane. Sometimes it's below the plane of the ecliptic, and sometimes it's above it. So all the planets that we've been talking about were like this. Okay, so let's say the sun is in the middle, we're all orbiting like this, and Pluto's like, we're like, cool, little weirdo out at the edge of the solar system. Okay, at first it wasn't a problem. So this is the history of Pluto. Pluto orbits the sun every 248 years. It's a long time in the context of humans. So you can look at this place. This is called aphelion. You don't have to memorize that. That just means it's when it's the farthest away from the sun. The last time that Pluto was at aphelion was the end of the US Civil War. Okay, here's the birth of the person who would end up finding Pluto. This is the birth of the person who the Kuiper Belt is named after, Gerald Kuiper. Wait, hold on. This is the wrong one. So this is Clyde. This is the guy who found Pluto. This is the guy whose observatory he used. And then this is the discovery. So Pluto had just gone a little bit around before it was found. Oh, here's the launch of Sputnik. So this is the space race. We landed on the moon. Then we discovered Pluto had a moon. Its moon is called Charon. Okay, and that's even before it gets the closest that it'll get. So before it made one rotation, or one half rotation, here's one half rotation, right? It went through this entire process. Okay. Then in 2006, we launched a spacecraft to go say hi to it. We'll talk about why we did that in a few seconds. It arrived in 2015. That's some cool pictures, which you might have already seen. And it's headed towards just outer space. That spacecraft is just flying away. And by the time that it gets back here, it'll be 248 years later. So it was discovered, became a planet, and was demoted from a planet before it even went around the solar system. Kind of weird. Okay. Pluto's kind of a weirdo. So I already told you that it's sort of tilted, but it's also like just showing a weird part of its access to us. So here's the sun, and this is the Earth, kind of doing, this tilt that we know and love, with the moon more or less going this direction. And so we orbit like this, and the moon kind of orbits in the same direction. That's not what Pluto likes to do. Pluto's a really big fan of having its moon go this, right? So as it rotates, the moon goes like that. Does that make sense? Okay. And that means that it has really crazy seasons. So because it gets closer, as it gets closer, its surface gets warmer. Just like if we got closer to any other fire, our surface would get warmer. Then we go farther away, it gets colder. Good. So we have long global cooling followed by short global warming. This is not the global warming we think about. No cars on Pluto that we know of. It's this intense period of additional heat, which is going to drive a lot of the seasonality. Okay. Questions? Yeah. Very good question. We'll see. Okay. Why doesn't it run into Neptune? Sometimes it's closer. Yeah.
It orbits 2 times. That's Neptune. Orbits 3 times.
Other way around. Almost. Yeah. So Neptune orbits twice. Every time Pluto orbits 3 times. Okay. That's what it looks like. Kind of cool. So here's Pluto. Well, when I made these slides 6 years ago, So Pluto's headed out now on this part of its journey. And Neptune is on the other side. So every time that they come close to each other, sorry, let me say that differently. They never come into a situation where they would come close enough. Like if you were to look in this region, Pluto would be here and Neptune would be here. By the time Neptune gets over here, Pluto's like way over there. Does that make sense? So they're in orbital resonance with one another, just like Io, Ganymede, and Europa were. Okay. And if you let them sort of play out this fun dance, this is what it looks like over millions of years. It's kind of pretty. We kind of move around. Pluto's orbit will just shift around as Neptune moves around. Okay. So Neptune is really shepherding Pluto. Pluto's not really its independent boss like you would think it would be. Okay. Here's another thing that doesn't really work. You go big, smaller, but still quite big. Uranus and Neptune, quite large, and then just paltry small, teeny tiny baby. Okay, so what happened? Something different happened, right? This is not like this, right? And these are the best pictures we had of it. So this is the reason why we had to go there. Or this is the reason why we convinced the American taxpayer that we had to go there. Because this is the best picture we had. Highest resolution. Remember, we have Hubble, very expensive telescope flying above. It can see galaxies beautifully. It can see like really, really far away, but it can't see this. Why can't it see Pluto well? What are the two reasons? Really far? Small. Pluto small. It's easy to see things when they're big and they're close. This is both far and small. Yeah.
And it also be because since it's far away, it doesn't have to get enough sun to get reflected off of Pluto itself. And it's like awesome for us to see it.
Yeah, so we'll see it's kind of crazy. When we see the pictures of Pluto, you'll be like, that's illuminated by the sun? What? How's it possible? It's so far away from the sun. How is the sun still that bright? The sun's really bright. Really, 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 really. Even though, like, if you look up today, you see how big the sun is in the sky. Obviously, it kind of makes a lot of sense. You're like, well, I get why everyone's bathed in sunlight. You go out to, say, Jupiter, it's smaller. And you go out to, say, Uranus and Neptune, it'll start to look just like every other star in the sky, but it'll still be really bright. Does that make sense? No, not. I'll show you. Okay. So if you take these and you put them onto an image like that, really good resolution, right? You can totally see its features. Can anyone see the sort of geologic features that we have here? No, that's a joke. You can't see anything. These are horrible pictures. Okay. And this is what it would look like. So here's the Earth at 5 kilometers per pixel. And this is the Earth's moon at the same resolution. So you wouldn't be able to tell anything. You can't tell that there's craters. You can't tell that there's lava plains. Gravity. This is the best map to put up. Kind of horrible, right? Okay. So what we had to do is we had to go there. Hold on, let me go back here. Wait. Okay, did I do this in the wrong order? We're gonna see if I did this in the wrong order. All right. This is the best map of Pluto. We got these pictures here where you can add color. This is also with Hubble. And you can like watch it turn around. And there's these dark spots. And there's these light spots, and some of the light spots are like yellowy. So we're thinking to ourselves, okay, what are some types of bodies we've seen in the outer solar system? We named a lot of things at the beginning of class. Let's name a couple of those outer solar system objects with surfaces. Io. Io was yellowish with dark spots. Okay, so maybe this is like an Io looking thing somehow. Okay. Do you remember what this one is? You don't have to memorize this. So this one up here is The moon. What's this one? There. Okay, that one's a freebie. This one on the bottom left is looks like a cantaloupe. You remember? Triton. Triton. So Triton is the cantaloupe, and Triton was a funny one, because it had some sort of weird features. So it had this like reason I called it cantaloupe in the first place. In the bottom right hand side, it looks like the surface of a cantaloupe, but it's not. There's space cantaloupe. But look, it also got this dark stuff, right? And the color here is like that yellowy color. So we do know that moons can have this like very non-white color if the ices are not made of just water ice. So Triton is the largest moon in the Neptunian system. This one orbits a weird way. Maybe this is the one that people were talking about, one that orbits backwards and is going to be destroyed. So as it gets too close to Neptune, it'll be pulled apart and Neptune will have a beautiful ring. Isn't that cool? Okay, no one cares. There's another picture, cantaloupe skin. What are these black things, by the way? Right, another way to say that is volcanoes. What kind of volcanoes? Ice volcanoes, cryovolcanoes. Okay, so these are, trapped material underneath the surface, finds its way through the ice, explodes, and then creates this like dark pattern. And if you're asking yourself, why does it look like it has like a, right, does it look like it kind of goes back like that? It's because there is a very thin atmosphere and there is wind. Crazy, right? Okay, tectonic features, lack of impact craters, fresh surface, black streets similar to volcanoes. This is not a picture. I mean, it's a picture, but it's not a real picture. This is an artist conception by Joe Bergeron, maybe? I forgot how to say it. Okay. So this one here, we talked at the very beginning. What is the Kuiper Belt? Well, it turns out that after we found Pluto, we started finding other things. And that's basically the ultimate death of Pluto as a planet. You get it. So essentially what happened is Gerald Kuiper, person who was born before Tombaugh, said, you're probably going to have a lot of icy asteroids. Okay? And he said it's going to be past the orbit of Neptune. A bunch of little icy pieces left over from when every planet formed. You're just going to have chunks of ice. Okay? And in 1930, this was the first object discovered in the place where he predicted these pieces of ice to be. Okay? We talked about that picture of Clyde Tombaugh looking at those two images, and you had to spot the difference. So with the advent of computers, it makes it a lot easier. So you just stack those images right on top of each other, and you look for the stuff that moves. So, you can see the one with the arrow, hopefully, right? Where's the one on the right-hand side? Top left? Tell me where to go. Oh, okay, good. All right, keep happy. Good, a lot easier, right? Found a planet. Well, it's not a real planet. But this is the planet hunting team of Mike Brown. Forget what their first names are. I found that. So they do this. They look for planets. They're looking for planet 9. I don't think it exists. Whatever. So at first it wasn't a big deal. Okay, you had the moon, you had the Earth. Pluto was big. And we found these other things like Sedna and Quar. I know that I'm gonna butcher a lot of these names. I'm gonna try my best, but if you know how to say them properly, just slide right in. Okay. So these were smaller. And so it's like, okay, cool. So maybe Pluto's like the king of the planets out there, right? It was found first. That's but that's not really true. You see a planet here. Where's it? It's here. Yeah, that's not good. Man, how good you are at finding planets. Real easy, right? Why did this take so many years? Okay, so here's the largest known Kuiper Belt objects. Okay, you started finding more and more of these objects. So that's Eris. I heard that at the beginning of class. There's Pluto, and it's got a moon called Charon. There's Makemake. I'm not going to try to pronounce that. There's Haumea. Haumea is funny. It's not even circular. It's like a little bit of a roly-poly. There's Quar. There's Sedna. We just saw those two. There's Orcus. I'm not going to say that one or these other ones. Okay. So all of a sudden, Pluto's not alone. Right? And now this idea, okay, so well, if Pluto's a planet, is Eris a planet? Because Eris is bigger. No one's pro making Pluto a planet, right? Okay. We've all given up on Pluto. And so this is basically the issue that they had. So we want to think, okay, Pluto was weird for a number of different reasons. It wasn't like the giant planets. How was its orbit again? Tilted. Okay, so what about these? You expect them to be in the plane? No, because that's not how I phrased the question. Okay. So they're in fact not in the plane. They're all tilting. And some of them are crazy tilted. So this is Eris. It's like, and then it comes back in. It goes way back down. Okay. And these ones up here, Haumea and all the rest of them, they're just doing who knows what. Right? So we don't really know what's going on with them. We haven't talked about how they formed or anything of that sort. And we just kept finding things. We're just so good at looking at these images that now we have these. Oh, geez. Okay, so here's up at the top right-hand side, and I'm really not going to try to do too many of these. There's Pluto. Okay, that's the one you know. Eris is bigger. So when you say, what's the biggest planet that's not a planet? It's Eris. Good. There's Makemake, Sedna. What are the other ones I can say? No, that's it. Okay. So there's thousands of them, and they're varied. And even when you look in the asteroid belt, you have this thing called Ceres. And that is like comparable in size to these objects. So then the question becomes, do we need to call Ceres a planet? Huge asteroid, it's like spherical, got a little white dot on it. Now I know what that white dot is. Is it like light calling us? Like, we're here. Yeah. Yeah. So white in astronomical context almost always means ice if it's a surface. Very reflective, right? Because this is dirt and dirtiness, and that's ice. Cool. And we saw this is great. This is raw images of how bad they had to deal with these. But what would happen here? This is going to be really hard for me to explain. You take a telescope, take a picture, and instead of it showing up on a CCD, like on your phone, they used to be on chemicals. They used to expose a chemical. And then they would print it off like a negative. Is anyone alive for, well, I know a couple of us are.
Like a Polaroid?
Okay. Before that,
Okay.
go before Polaroids. Yes, like imagine with the darkroom. But you had to do this for every single image. So when we're thinking about Clyde looking at these pictures, talking about exposing one, then bringing it into the room, and then exposing another many years later, and trying to look at these physical pictures side by side and look for a difference. Right? To find Pluto. Okay. And that's what gives this weird shape. So this is Pluto. And these little dots here are just like stray light coming through the atmosphere and then hitting the surface and making these little pieces. And this is negative, so the colors are flipped. And then you look to the right-hand side and say, well, it's not so circular anymore. What's happening? Almost. It is something to do with gravity, but
doesn't have enough gravity to.
No, it is in fact round right here, and it is round, but it has a friend. It has a moon, Charon. And what's happening here, Charon's behind it, and then Charon's right next to it. And it makes it look lumpy. Okay? That's the relative sizes. Okay? Okay, so there's Great Britain. Got rid of them. Also, that's the relative size of Great Britain in the US. The fact that they ever thought they were gonna win is absurd. So here's the eastern seaboard, and that's about the right size for Pluto, like from here to here. So if you've ever driven from, say, Florida to Boston, takes like 20-something, 40-something hours. So that's like driving from one end of Pluto to the other. Right? Pretty cool. Bring your Tessie out to space and drive. Okay. They kind of do funny things together. So here on the right-hand side, they're very close. And so just like with our moon, which always shows the same face, they both only show each other the same face. And they spin around each other really quickly. So this is, what is that? Oh, shoot. It's a fun job. They move around, they spin around each other and rotate 6.4 days. Okay, so their day is, sorry, let me say this properly. Their day is slow, but their orbit around one another is quick. Does that make sense? Okay. And if there was an atmosphere, what would we expect to have in the atmosphere? Turbulent storms? Yeah? With a 6.4 day rotation? No. Turbulent storms? No. Calm, right? And it's also far, not a lot of energy in the atmosphere. Okay. This is the weird thing that it looks like. So looking from the late 1980s, so it looks like this, it's orbiting in this direction, it's spinning, and Charon's coming towards us, away from us, and towards us, and away from us, like that, every 6.4. So it's doing this. As it's orbiting. Kind of wild. Because of this, Pluto doesn't just sit there. Pluto's also orbiting Charon in what's called the binary system. So they're doing this. They're falling around each other. And it looks like that. So it looks like it's moving around in a little circle, and this one's moving in a big circle. Okay. And you can do this really fun thing where you can watch a star disappear behind the planet. And the way that the light here on the left-hand side, this is the combined light of the star and the planet as they're separated. Right? So here's the star and the, I wish I had my baseball. Here's the combined light of the star and the planet. And then when the star, or when the planet passes in front of the star, it gets rid of that light. Right? Because the planet doesn't let light through. Okay, everyone gets that? Just make sure we got that. Okay, so then it goes down to 0. But on the way down, part of it is going through the atmosphere. Yes, so there is an atmosphere. And you can see what it's made of. So they looked and they were like, it's very cold. 50 degrees Kelvin is very cold. And it's about 50 times, well, 50 microbars. Remember that a bar is the pressure that we're at right now. A micro is 10 to the minus 4. So this is, well, you can do the math at home. It's small. Okay. So they thought it probably looked like this. There's probably this big atmosphere. Even though it's 50 degrees Kelvin, that's not super hot, so the stuff isn't flying away. So they have this thick atmosphere, sorry, this thin, large atmosphere. And Charon probably is running through it, and it probably looks like a comet with a very gross surface. So as comets go through the solar system multiple times, their surfaces become rocky and boring and brown. Okay, so that's what we thought. Okay. We thought that this stuff would get impacted by the solar wind, and that was like a way to lose that atmosphere, and probably very boring. Okay. Any other expectations you have for it before we send spacecraft there together. Has anyone already seen these pictures? Cool. Awesome. Okay, so we launched New Horizons. I personally did it. No, I'm just kidding. Humankind launched this spacecraft. This is my favorite part of the spacecraft. You don't know what this is? What was that? So this is a good question. Can I use solar panels past, say, like Jupiter? Not really. So the size of the solar panels for very, sophisticated instruments gets to be so big that then the cost of bringing them out there is really expensive. So what do you do instead? Can't use gas, right? Not just because it's climate change. What do we use instead? Battery. Yeah, we'll need a battery. What kind of battery? Not lithium. We will use batteries on board, but they won't be powered by something. They need to be powered by something, right?
Isn't it, the gravity by the planets, like if it's 60?
That will adjust how it's moving. That's true. But how do I turn the computers on? I'm gonna boot up my Mac and the games. That is a nuclear reactor. It's kind of cool. So it's not attached to the bus. They stick it off to the side. And these things here are radiators. And so they're letting off the excess heat because you basically have a weapon on the side of this. So what they do is they have some cabling in here that's warm, and that provides the heat in the battery. So they use basically the heat from the nuclear reactor to power your spacecraft. Okay, fun, right? Well, as long as it's not on Earth and as long as it doesn't explode on the pad, we're good. Okay. So this is 2003. They designed it. This type of work is really cool if you're into engineering. I'm not, but that's why we're gonna move past it. Here's the green room. Or sorry, what are they called? The white room? There's a specific term for these places where they put on the bunny suits. You go like these white suits that are electrostatically charged, and they go in and they fix every single wire. All of this like gold foiling is real. You just expose all your electronics to space when you're in these types of rooms, because why would you bring up extra material just to cover your wires? Silly, bring the wires. That's all you care about, right? You do fun things like spin it very fast. One of my favorite stories of all time is about the worst day you could possibly have working as a spacecraft engineer. Do you know the story already? Okay, this is called a spin test for obvious reasons. What you do is make sure that when you're spinning, that pieces on the spacecraft don't fly off, right? Makes sense. So this is about $1 billion spacecraft. Spin test goes really well. But they do this with all spacecraft because as the rocket goes up, it's rotating, stuff happens, you want to make sure it's not rotating. They put it on this little platform. It's a spin platform. And you got to hold it in place. You got to put the screws in. Okay. So someone was running a spin test on a different spacecraft, and they're like, I don't have my spin, my screws. We borrow them from this spacecraft over here. They borrowed them, brought them over. They did their spin test perfectly. Everything went well. And what did they forget to do? Put the spin, and so the other person goes to spin up the other spacecraft, and it falls over and is destroyed. $400 million accident. Because by the time it gets to this point, it's already built, right? If you drop it, it's like the worst Lego set you've ever built. Okay, so that's when you have a really bad day at work, just remember this story. At least you've never single-handedly broke a $400 million spacecraft. Okay, here's a bunch of instruments. I won't talk about all of them. This one here is really cool. This is the student dust counter. This is actually built at students, built by students at Colorado, where undergraduates went into a lab working with obviously experienced people to build this type of dust counter that's going to look for how much stuff is in between us and the moon and then Pluto. The rest of these are super boring except for things like Lori. Lori is what we're going to do to see. Ralph is also used for seeing. Ignore these words. Anytime you see this type of word like Pepsi and swap, like solar wind. Ugh. I don't want to hear about electrons and ions. Show me the pictures. Okay. There's Lori, high resolution black and white images. Swap gross. Student dust counter, cool. Those are the students. They look older than that now. They look old then. Here's the spacecraft. And they were getting ready to launch. They're going to go on Delta Heavy. This is gonna be the fastest thing that we've ever launched from Earth until I think like a year ago when Bepi Colombo was launched, and that's headed towards Mercury. Sure, I'm running out of time. Okay, so this is basically what we wanted to do, and it's crazy. Can I explain to you how crazy this is? Okay, here's Pluto and here's Charon. And we're gonna fly between the orbit of both of them. And then we're going to pass behind Pluto and then behind Charon. How far away are these things again? Super far. How many tries do we get? Just the one. If you're off by half a kilometer, 2 kilometers, you just miss it entirely. So the fact that this was successful at all, amazing. Okay, we're actually going to study multiple objects as they got closer. They kept finding moons. As you get closer, it gets easier to see. There's a whole host of stuff. So those are the two we talked about. That's where we're going to aim. And there are all these other ones: Nix, Kerberos, Styx, and Hydra, all named after these underworld gods, right? You familiar with that? Pluto is the god of the underworld. Yeah. Okay. And that's how big we think they are. Teeny weeny babies. So they're kind of just like whatever they are. And this all happens in such a short amount of time. You're moving at 30,000 miles an hour. So you fly by, this is the closest approach. And then 14 minutes later, you get the closest that you get to Charon. And then 50 minutes, you pass behind the planet. And then you pass behind the moon at I think that like 2 hours. This whole encounter is like a couple of hours. Then you fly by carbon. You have one chance, 2.5 hours of observations, and that's it. Right? Worth it? What do you think? Would you try? No, I wouldn't even try, right? Okay, well, you can't slow down. So this is the only way to do it, right? So they launched, and what do we expect Pluto's surface to look like? Based on what we've learned so far in this class. A, smooth ice-covered surface. B, heavily cratered ice-covered surface. C, volcanically active rocky surface. D, thick Jupiter-like atmosphere surrounding a small ice core. E, thick Jupiter-like atmosphere surrounding a small rocky core. You know when you're ready? Let's vote on 3, 2, 1. Okay. All right. So very few people took my my bait questions. Doesn't have a thick atmosphere because it's not Jupiter-like. What about these 3? Anyone want to defend these? Yeah. You don't think it'd be heavy cratered? You think smooth ice covered surface? Okay. Okay. Anyone have different ideas? Okay, everyone agrees smooth ice covered surface. If you don't see, and if you say anything different, we'll be shocked, right? Okay. So there's the Pluto predictions. My favorite part during this time, everyone who's working on Pluto, grad students, scientists, whatever, they try to get the papers out as quickly as possible before they actually got there. You have some predictions, but you try to publish them. So that way you could be like, okay. Otherwise your people just get totally forgotten. Right? So you put out the most outlandish predictions you could. Okay. And here's a question you maybe won't know the answer to. The temperature of Pluto, 40 degrees, minus 233 degrees C Celsius. No, we don't use that. What state of water do we expect to find on the surface? A solid, B partially solid, partially liquid, C fully liquid, D partially liquid, partially gas, or E fully gas. Let's vote on 3, 2, 1. Okay. All right, so we have some, basically everyone wanted one of these. Pluto has a density of about 2 grams per cubic centimeter. So if water is 1 gram per cubic centimeter and rocks is between 2 and 3, and metals are 5, what do we expect it to be made of? If I told you it was ice all the way through, would that be okay? Well, its density is 2 grams per cubic centimeter. So it can't just be ice. That would be ice and something. Does that make sense? How I made that? This might be important later. Okay, if I have an object and I tell you its density, I tell you roughly its size. Okay, small, density slightly larger than water. Can it be made only of ice? No, density is not high enough. It has to include rocks or maybe some metals. Feel like a metal core, ice on the outside. Okay. I already said that. Okay, wait, hold on. Wait, what happened here? Okay, here we go. So these are the pictures as we get closer. Okay. So on the top left-hand corner, June 5th. And then I think it goes like this. And then for some reason like that. I don't know why I said that. But what you're going to be seeing here in the next few seconds will be a close approach video. But it's all of the observations stitched together. Okay. Excited? Excited?
Yes.
Yeah, let's go. Okay. So these are the real pictures. And that's the atmosphere as seen from behind. That's us passing through shadow. And you kind of saw it on the way in. We'll see it again here. This is all we got. Really close. Do you see Karen in the background? That's all Karen got. Now, thankfully, we had multiple cameras looking at the same time. This thing keeps playing. It's one of my favorite. What do we see here? All right, you got to put on your like quick hands. What do you see? A heart. Smooth. What else?
Brown.
It's got an
It's got an atmosphere.
It's got an atmosphere. It is brown, but the atmosphere is not brown.
Because like a black or darker.
Yeah, it's got a darker area.
Like the
Kind of reminds me of the moon, right? Kind of weird like that, right? Okay, so let's look at this thing. It's a complex ice flow. That is the Pluto. That's the still frame. Click. This is in something called enhanced color, where it's showing some of the mineralogy. Okay, so things that are similar minerals are going to be the same color here. I'll show you another version of the same picture. That's the actual true color. And there's this heart. Huge heart. What's interesting about that heart? Other than it's cute. It's white. It's white. Good. So that means it's icy. Yeah, very good. What else?
On top of it, the left side is more like, I think gold, and then the right side looks like it has, as if it's melting almost, like when the frost or something's kind of coming off.
You think this side is more like melty?
No, that one's not full. The
Okay.
right side is more like it looks like the ice is more dispersed in some areas compared to the left side.
The left side is in the country borders.
Not just water ice, okay. Okay. Can you like, you guys identify water ice by eye? I can. We're gonna come back to that idea about what ice is like. It's definitely ice. I'm not gonna give you that it's water ice yet. Anything else? Think about it in terms of our our geologic processes. I already gave one away. What are the geologic processes? Okay, so okay, so do I see tectonics?
Yes,
Where?
on the bottom left,
On the bottom left.
yeah, where that.
Get you all laser. This
Yeah,
one
but
here,
it
right?
does.
And then you like point out. Yeah, also here on the right. Okay, what else? We got one, there's three more.
Impact crater?
What's that?
Impact crater?
Impact crater.
Specifically that one little dot right there, well, not little dot, like you can see the layer on the bottom left,
This one?
yeah.
Okay,
It's
Okay.
dark and you can see like.
light underneath
Light
that, right?
underneath.
All right, cool. What was that?
That could be a cryo.
Okay, so we don't really know whether it's cryovolcanism or potentially volcano, impact cratering. Good. And what's the last one? Erosion. Do we expect erosion here? I can see a little skepticism. I like it. I like it. So we say no because it's small and cold, and its rotation is like very, very slow. But maybe we won't be surprised. Okay. So in fact, you're right, there is ice here. And that's because this is what we think the density looks like. We think there's a lot of rock, and there's a giant amount of water ice. Then there's this layer of frozen nitrogen. And above that, you have this chunky crust. So before we really thought about this in terms of like core and mantle and crust. And we're going to replace those ideas here with what we have. You have rock, that'll be your core. Water ice, it's frozen, but it's like frozen mantle, more or less. And then the crust out here is the frozen nitrogen part. I'm going to bring you back to this in a few seconds. Okay. Here's a map of the whole surface. Gets fuzzier as it spins around. We didn't get to see the whole thing. We got to see a lot of the top. This part we saw the best. And then this part, you know, as you're getting farther away, the resolution gets worse. Okay. You had 2 hours, we had 2 hours to fly by. It takes 6.4 days to spin. So we didn't get to see the whole thing. We'll fly another one in a couple of years, like 40. Okay. If we look closely here, this is called Sputnik Planitia, or at least that's the name that they threw out there. I really want to focus in on this side. What am I not seeing that I would normally see or expect to see? Craters. How many craters do I see on that left-hand side? 0. 0. How young is that surface? Very young. Very young. Very young. Less than 60 million years. It's like brand new. We just saw on Mars stuff getting hit. Like today. Mars is dead, but this surface is still getting hit. This thing is not getting hit, or is getting hit, and something else is happening. Anyone else can imagine what's happening here on the left-hand side? Yeah.
The heat from like when it gets hit causes everything to melt and it causes it to smooth over.
Okay, that's a very good explanation, right? But then why are they over here? I like that. And in fact, smashing into different substrates does have a totally different effect. But what it ends up doing is usually just smoothing out the whole.
That reminds me of like your
This does? Like in
Yeah.
the way that it's moving that way? Yeah, I like that analogy. It looks like this is like a flow. Does it look like a fluid to anyone?
That reminds me more of like the ice in the like in the Arctic Circle where it's like kind of breaking apart.
Oh, interesting.
Like effectively because the ice like breaking apart and drifting.
Okay, so you're thinking that these are like individual ice flows, like when the penguins jump from one to the other? Is that what you're thinking?
Yeah.
Yeah, okay, all right, let's see if we can find an analogy here. So this is the structure that I really want to focus in on. No cratering at all. There's these little things in here, actually. What do you think those are? What if I told you they're mountains? We're gonna come back to that in a second. Here's a picture from the side. Isn't that beautiful? Okay, this is less than a few 100 million years old, this entire region. And this region, we call it Hulu Regio. This is dark and scary. Is much older, potentially like 4 billion years old. And they're just sitting right next to each other, hanging out. We can tell that it's much older because it's just filled with craters. Okay. Someone's job was to figure out whether it was cratered. They went in. We showed this from Mars. Remember that grad student who did this?
Yeah.
Someone went in. They did. They counted every single one they could find. And these are the regions they didn't map, obviously. But this looks weird. It looks very unusual, right? And when I look at a picture of this, I see these ovoid segments. I just can't help but thinking of soup. This is convection. This ice is convecting. Okay? And it's making these little symbols like ovoid shapes in the ice where it's sinking and then rising in different places. Okay? So this is what the picture looks like. You have this large pool on the bottom here. You have nitrogen ices being recycled. And that's why you have no impact crater. Soft mantles being recycled. Does that make sense? This thing I told you I'd come back to. These little mountains here. So at 50 degrees, ice doesn't really act like ice at all. Water ice behaves like a rock. Like you could stand on it, you could kick it, and it wouldn't just shatter. Now this type of ice here, the nitrogen ice, a little softer, a little more pliable, turns into the type of object you see. So this is like an H2O, a water mountain, in a field of nitrogen and carbon monoxide ice. Which is really crazy. You see things that look like icebergs or the equivalent of icebergs. And the way we think about this is kind of like how we think about it in the Antarctic. So we see these rocks, and then this is like actual water ice on the earth. We see these all the time. You can see how the ice moves around it very slowly. I mean, ice you don't really think of as flowing, but on geologic timescales, it does flow around hard objects. Okay. And you can watch in these pieces up here, how it seems to be sort of nitrogen ice is like flowing around these. I think one over here was talking about how it looked like it was like magma pit, right? Exactly what's happening. Cool, right? What do you think that is? Be respectful. Does it look like an impact crater? No, not really. We think this might be a cryovolcano. Extinct, but potentially a cryovolcano. This is a very similar shape. It's got like this moundish structure. And then it goes down into this hole. And of course, you get one flyby, so you don't get to go look later and see if there's a plume of material blowing out of it. But this could potentially be a cryovolcano. And if you're looking really closely, you might see other stuff too. Anything else sticking out to you in this picture? Hey, what about this picture? Tectonics, yeah, okay, cool, tectonic feature here, definitely. Smaller feature.
The dunes.
Dunes. Dunes. That's what this is here. Can you believe that? That is not something that I would have guessed. There are dunes on Pluto. Now, it does have an atmosphere, so maybe that's not so surprising. How they get to sort of pile up nitrogen ice, which is rolling around on the surface, acting like a sand type thing. I'm not a geologist, but it's pretty cool. Okay. All right. And you know what this is? No.
Uh, That impact theory?
Yeah, it kind of looks like it would be evaporating, right? Like, so maybe like stuff like smashed into the ice. It does look like someone was walking, like snowshoes on, right? What? Or was it moved?
I
You,
don't-
oh, you seeing these streets here, right?
Or like the one on the upper right corner. Those little.
These little things, they dragged.
I just think it's weird that it's only in that part that has those, like it starts a little bit towards the middle and then towards the corner of it, it's like all clustered together.
Yeah, yeah,
And then
definitely.
down there, it's smooth. Like, it's
Definitely,
just like-
definitely.
Is this-
Right. No, it's not dunes,
I kinda
but it
think
is an
so.
aeolian feature. Okay, they are called sublimation pits. And they're very similar to what we'll see on comets. What happens is you have a porous material of rock and ice. And the top part of it starts to evaporate. And it shows, it lets light down in to a place where there's more rock and ice. More ice than rock. And that ice gets really hot and starts basically blowing out of the pit. Isn't that weird? And then it becomes this really beautiful thing called the atmosphere. So this is the picture taken from the side. Sun is illuminating it from this direction. Anything standing out to you here? Other than it just looks fake, like it looks like the surface of some candy. Mountains, yeah, look how gorgeous these mountains are. This is like a real mountain. You could like go hiking up here. I mean, it'd be cool, but you could do it. Remember when we talked about it at the beginning, you're like, there's not enough light? It's like fully illuminated. The sun looks like a dot, folks. And yet you could be walking around here like, oh, doodly doo. Sun's bright. Yeah.
Are those white streaks supposed to be the atmosphere?
Yes. Yeah, so these white streaks, you're talking about these ones, right?
Yeah.
Okay, what do you notice about them? Yeah,
It's like a lot of layers.
a lot of layers. Layers, so that's really good, because layers tells you that it's
Made up of different gases.
maybe not necessarily different gases, but that it's structured, right? And it's calm. Okay. These are the water ice mountains we talked about before, cold surface temperatures, methane ices, carbon monoxide ices, nitrogen ices, atmosphere visible. We talked about the fact that it has a big extended atmosphere. And sure enough, we got close, we can see how big it was. We went right behind it, and see how large it was, much bigger than we thought. This is the relative size. So on the left-hand side is, on the right-hand side is the Earth. And the Earth's atmosphere. We talked about this thing where like the Earth, if the Earth is a basketball, then everyone you know and love is on a piece of paper on top of it. That's how thin the atmosphere is. And in the same analogy, Pluto is this tiny, tiny little thing, but this is the top of the whole atmosphere. So relative size, Pluto's atmosphere is larger than the Earth. Why is that? Well, because it's got a low gravity. So any gas that can try to escape, let's say it's going, whee, whee, right? That makes sense? They don't necessarily make that sound, but whereas here, you try to escape, you fall right back in. Right? Or if you get enough energy, you here you get enough energy. Okay, still part of the atmosphere. Sort of a weird way to say the atmosphere. Right? Okay, I'm running out of time, but this this is not working. Oh god. Sorry, that was like 7 in a row. Okay, so we talked about the ordered layers. Let's not talk about what it's made of, but it's made of hazes. That layering that you were seeing before, they're very complex, like long chain hydrocarbons. Just comes from the fact that you're getting energy from the sun. You're turning nitrogen and methane into the weird stuff. Okay. And here's its friend. And that's the one. I mean, we have enough time to probably do a little bit more. Okay. Yeah. Here's his friend Charon. Charon's got like a little hat. A brown hat. Why does he have a brown hat? What?
He's a gentleman.
Not a bad answer, but not the answer I was looking for.
Does it have to do with the fact that it spins?
Yeah, so it spins with Pluto. Pluto's got a big old atmosphere. This atmosphere's got haze in it. This is stinky Pluto haze. Smashed onto the surface, coating it. So they show the same face to one another constantly. And that's the haze face. And Charon has complex geology. It's got what types of things do you see here? Cratering, tectonics, fractures, yeah, fractures here, right? Like a cracked egg. No atmosphere, as far as we understand. 0 atmosphere. Let me ask you a question. These are 2 objects with atmospheres. Which is which? One of them is not the Earth. The left is Pluto, good. What's the coolest planet that's not Earth? No. Yes. Yes or no? What's the coolest moon that's not our moon?
Io.
No. It's blinking. Titan. What does Titan have on it? An atmosphere and liquid on its surface. Lakes. Okay, so this is Titan on the right-hand side. And Titan and Pluto actually have very similar atmospheric layering. They have these haze layers. Okay. Boring. So this is to get to the end of the story. Pluto's just one object in the Kuiper Belt. There's thousands of them. New Horizons is headed towards the second one. So the way to really think about this as an endeavor is that this is the first time that we've seen a Kuiper Belt object up close. They're hard to get to. We don't do them very often. So this one we wanted to get a lot of information on. It was pretty cool. A lot of unexpected stuff. I don't think they made it to this one. So this was supposed to be the next potential target when I first made these slides in 2016. And yeah, it's hard to find objects. Okay. How much did this cost? Anyone want to guess? Guess out here. You don't have to like put your finger up.
300.
Say that again.
300.
300 million. So what did you think you paid personally for New Red?
Me? I probably.
Okay.
I'm kidding, I think
The hypothetical human who might be in this room. What did the American taxpayer pay on average for this mission? How much? $3. That's pretty cool, right? With just $3, you too can go to Pluto with us. Okay. So we're going to talk a lot more when we begin to talk about asteroids and comets as a whole. But this is basically why we wanted to go to Pluto at all. It's the first step to unlocking the Kuiper Belt. And that's object we're going to talk a little bit more on Tuesday. Any questions, comments? Yeah.
So if Pluto had dunes, does that mean it had erosion? Create the dunes?
Yeah, probably. right? And so we see, if we look at the surface in more detail here, the crater rims are sort of degraded. And right, so you can see even in here, this surface looks like, yeah, fluffy, right? If you think about a terrestrial ice, they look hard. And this looks like it's got little pieces on it. I mean, this region over here, it looks like you could like ski in it. Yeah, in a nitrogen snow angel.
I mean, it has wind.
Probably not strong wind, but that's a very good question. You know, there is pressure there, right? And we see that in the atmosphere. It's a physical atmosphere with layers. You can't have layering unless you have different like densities as you go up, right?
So it would be strong enough to create wind though.
Exactly. Yeah. So, but you can push small pieces of ice. Ice small. If you stood there, you probably wouldn't notice anything, except for it's freezing. Yeah.
So it sounds like the plate that you're gonna start, does that mean that they could put? Alright, do the solar winds affect the atmosphere much?
Yeah. So they penetrate right through.
Okay.
That's what's giving you a lot of your heat. That's what's heating the atmosphere at cold.
But for that.
But it's also really far. So the amount that you're getting from the sun is down compared to like at Mercury.
Does that mean that it's that it would take longer to get to the solar wind or?
Yeah. So, but its atmosphere is probably being replenished. The fact that it's icy, right? It's losing stuff from the surface. And it might have cryovolcanism that we totally missed. Right? Oh, I'm glad you know. I have a.
But it's only gonna pay $5.
I put it on the schedule for 2 months. I put one for the 8th and I think one for the 7th. One for the 7th, the Monday, 2 on Monday, the one on Monday and the 28th. Ahead of yourself, we'll get to that. We'll get to that. We'll get to the punchline.
Yeah.